So how is it possible that a circuit built from just three simple components can have three, well, completely different personalities? It almost sounds like a magic trick, right? But it's the reality of what we call RLC circuits. In this explainer, we're going to demystify how these things work and, maybe more importantly, see why their behavior is so incredibly critical to the tech you and I use every single day.
All right, here's our game plan. We'll kick things off by meeting these three circuit personalities. Then, we're going to dig into the two critical frequencies that really define them. From there, we'll watch them face off in what I like to call the damping showdown. We'll figure out how to predict the final response, and then we'll tie it all together with something super practical, the clock ticking away inside your computer. Okay, let's dive right in. The number one thing you've got to grasp about RLC circuits is that they are not a one-size-fits-all deal. Not at all. You can use the same three types of components, but depending on the specific values you pick, well, every single circuit ends up telling its own completely different story. And that story, it always unfolds in one of three ways. So let's just think of them as personalities. This is really the key idea that's going to guide us through this whole thing. For just a minute, let's push the complex math aside and just focus on understanding the character of the circuit. So what are we even talking about here? Well, an RLC circuit is, you guessed it, an electrical circuit with three key players: a resistor, the R, an inductor, the L, and a capacitor, the C. And that second order thing you see, all that really means is that the way these three interact creates a much more dynamic story. Think of it like a plot with a twist, not just a simple straight line from A to B. Okay, you know what? Let's just spoil the ending. These are the three personalities we've been talking about. First, you've got overdamped. This one's sluggish, kind of slow, like trying to run through molasses. Then there's underdamped. This guy overshoots the target and kind of rings like a bell before it finally settles down. And finally, critically damped. This is our Goldilocks circuit. It gets to where it's going as fast as humanly possible with absolutely zero drama or overshoot. So the big question is, what makes them act so differently? Well, the whole answer boils down to two competing forces that are always at war inside every single RLC circuit. Seriously, you can think of them like two puppet masters, constantly pulling the strings and deciding how the whole performance is going to play out. First up, we have the neighbor frequency, which we call alpha. And the absolute best way to think about alpha is to just picture it as the circuit's brake. Yeah, a brake. It's the damping force, mainly coming from that resistor and capacitor, and its whole job is to try and slow everything down and bring it to a stop. It's what controls how fast the energy in the circuit just kind of fizzles out. And fighting against that brake is the other force, the resonant radiant frequency, or omega naught. So if alpha is the brake, then omega is the spring. It represents the natural desire of the energy to just bounce back and forth, between the inductor and the capacitor. If you took the brake away, if there was no resistance, this thing would just want to oscillate forever and ever. So now we've met our two main characters, right? The brake and the spring. And with that, we can see the circuit's behavior for what it really is, a showdown. It is a constant battle between the force that wants to stop and the force that wants to keep bouncing. And this, right here, is the whole ballgame. The million-dollar question: which force wins? Because the entire personality of the circuit, whether it ends up being slow or bouncy or just right, it's all decided by the outcome of this one internal tug-of-war. And here they are, the results of the showdown. It's actually pretty simple. If the brake force is stronger than the spring force, the brake wins. The circuit is overdamped. It just kind of slowly grinds to a halt. Now, if the spring is stronger, the spring wins, and the circuit becomes underdamped. It bounces all over the place. But what if they're perfectly matched? Well, then it's a tie. And that's when we get that perfect Goldilocks, critically damped response. So you see, figuring out the personality isn't just for fun. It's not just a label, it is the key. Because once we know who wins the showdown, the brake or the spring, we're not guessing anymore. We have an exact blueprint that lets us predict precisely what that circuit is going to do at any given moment. And the process is basically a 4-step recipe. Step 1, you calculate your brake and spring forces, alpha and omega, from your component values. Step 2, you compare them to see who wins and figure out the personality. Step 3, you grab the correct math formula that matches that specific personality. And finally, step 4, you plug in the circuit's starting point. And boom, you get the exact final answer.
Now, I mentioned initial conditions in that last step, and I know that sounds super technical, but trust me, it's a really simple idea. All it is a snapshot of the circuit right at the moment the clock starts ticking. We're just asking two questions. What's the starting voltage or current, and how fast is it changing at that exact moment? That's literally all it is. Okay, so this is all really cool theory, right? The break, the spring, the showdown. But where does any of this actually matter in the real world? Well, I can pretty much guarantee it's happening inside the very device you're using to watch this right now. Yeah, this is not just a problem you solve for homework. Getting a handle on these three personalities is literally the difference between a smartphone that works and one that's a useless brick. It is fundamental to every piece of high-speed electronics you can think of. Your laptop, your gaming console, even the giant data centers that power the internet. And one of the most critical applications is right here. Designing a clock for computer timing. Think about it. Every single computer needs a heartbeat, a steady pulse, to make sure all its millions of operations happen in perfect sync. And where does that heartbeat come from? You guessed it, it's generated by a circuit. So out of our three personalities, which one do you think that clock circuit needs? It has to be critically damped. It's the only one that works. If it was underdamped, those bouncy oscillations would create chaos, total timing errors. If it was overdamped, it would be way too slow to keep up. You absolutely need that perfect Goldilocks response, lightning fast with zero overshoot, to create the crisp, clean, reliable pulses that run our entire digital world. And that really leaves us with one last thought. We've seen just how essential that perfect signal is for something as simple as a computer clock. So it makes you wonder, what happens in our digital world when these signals aren't perfect? It's a pretty powerful reminder that beneath all the fancy software and all the complexity of modern tech, everything, and I mean everything, still relies on getting the fundamental physics absolutely right.